Hello AP Physics student. This video outlines the 16 pages with examples in the AP Physics 1 summer assignment. Please use this video as needed to go over those example problems and learn how to do the complex work that we are doing in this summer assignment. Now let's go ahead and dive right in. Right, part one starts as easy as they come with hopefully what is a nice review for you in scientific notation. So you'll notice at the top I got these stars here. That is not the difficulty of these parts, but it is how relevant they are to the rest of the course. So some of these topics you're going to use a lot, and scientific notation is one of them. We deal with a lot of numbers, and a lot of them are very big, and a lot of them are going to be really small. So there's no way we can spend all that time writing all those zeros. We got to be able to express quantities in scientific notation. So the key part to what is official scientific notation is making sure that we have a value out front that is bigger than 1 but less than 10, and then we're expressing that times 10 to some value. So how do we figure that out? Well, in example 1 we have the number 820 billion. We want the number in front to be a value bigger than 1 but less than 10. So we move the decimal from the very end to be in between the 8 and the 2, and that would give us the number 8.2. We then count the number of spaces that we move that decimal. In this case, that is going to be 11 spaces. And then we write the whole number as 8.2 times 10 to the positive 11. So that is how we would take this value and put it into scientific notation. The two are then equivalent. We can do the same thing in example 2 with small values. So in this case, we have a very, very small decimal, but we want the number out front to be a number bigger than 1 and less than 10. We move the decimal to do that. In this case, we're going to move the decimal 15 spaces to the right to make the number 5.84. And then this time we have moved it to the right, and so that is going to be a negative exponent. So a lot of people remember, oh, if you move the decimal left, it's positive. If you move it to the right, it's negative. Just look at the number. So in example 1, we have a big number. We should have a positive exponent. In example 2, we have a very small number. We should have a negative exponent. And get used to just seeing these values. If we see a number in scientific notation with positive exponent, big, negative exponent, small. So very helpful to just have that related. And then finally in example 3, we have a number here that almost looks like it's in scientific notation, 154.8 times 10 to the 4, but the number in front is not bigger than 1. It is bigger than 1, but also bigger than 10. And so this value, we do still need to move that decimal 2 spaces over. And so we are going to end up with a result of 1.584, and then we add those 2 spaces that we moved to the already existing 10 to the 4, and so we get 10 to the 6. Now moving on to part 2. In part 2, we are doing metric unit conversions. Now, once you understand the trick of these, hopefully these will be extremely easy for you. Now, let me explain what that trick is. Now, the unit itself doesn't matter at all. So take example 1, we are doing kilonewtons to newtons. You see on the top there, all of those second letter, the base units are identified for you. And then what we really need to see is that prefixes table. Now the trick here is we are going to look to see what the difference between kilo, what the difference between the base is. Now all of these prefixes are expressed in terms of the base unit. So these factors are how much bigger they are than the base unit. So a kilonewton is 10 to the 3 bigger than the base unit of just newton. So the trick here is we have to think about, we are taking a large measurement, 12 kilonewtons, and we are going to measure in something that is now smaller. Well, when you measure in something smaller, you should expect that number to grow. So if you're having a hard time conceptualizing this for kilonewtons, think about this in kilometers and meters. 1 meter is just about a yardstick, while a kilometer is closer to a mile, and a kilometer is 1,000 meters. Now, if I measure 12 kilometers, that's 12 miles. That's quite a lot of miles. And now if I measure those in just the meter sticks themselves, you're going to get a lot more single meter stick measurements while doing that. So we expect the number to grow. So anytime we are moving down or we're making a measurement with a smaller we're measuring something with a smaller sample size, then that is going to cause the number itself to grow. How much is it going to grow by? Well, by that factor. And so the 12 can just be multiplied by 10 to the 3. So we could have the final answer of 12 times 10 to the 3, or to put it in proper scientific notation, 1.2 times 10 to the 4. Now you might be asking me, Mr. Williams, can I not just answer that the final answer is 12,000? You absolutely can answer it in 12,000. You don't need to answer these in scientific notation, but as we're going to see quickly on, a lot of these numbers will be very big or very small, and so scientific notation is going to come up a lot. Now let's see example 2. Now we're going to do 1.5 terameters to micrometers. That symbol there is the symbol mu, and that's our prefix for the micro. Now, a terameter is a factor of 12 bigger than a regular meter, and then a micrometer is a factor of 6 smaller than a regular meter. So what matters, we could do this conversion twice, I guess. We can go from terameters to meters, and then we can go from meters to micrometers. But what matters is the total difference from tera to micro. And if we just do that difference, and if you notice if the difference from 10 to the 12 to 10 to the negative 6, well, that's a power of 18, or a factor of 18 difference. Once again, we're measuring now in a smaller thing. So we have 1.5 terameters, which is an incredibly large distance. And now we're going to measure that same distance in incredibly small units. So we're going to get a much, much larger result, a factor of 18 larger. So our final answer is just going to be 1.5 times 10 to the 18. Hopefully you're starting to see the trick now. If not, let's do a couple more examples. In example 3, we have 190,000 pico-ohms to milliohms. Check out pico is 10 to the negative 12. We see that milli is 10 to the negative 3. So the difference between those two is a factor of 9 difference. And so now this is our first example of we have something measured in an extremely small unit, and now we're going to measure it in something larger. So now when we're measuring with bigger things, we expect the number to go down, and it's going to go by that factor difference that we already identified. So we can just take 1.9 or 190,000. We can divide it by 10 to the 9. That is the same thing as multiplying by 10 to the negative 9. If you want to do a quick and easy way that way, either way you do it, we would get a final answer of 1.9 times 10 to the negative 4. Again, if you got the decimal answer of that, which would be 0.00019, that's absolutely okay as well. In example 4, we see the kili to centi. So go ahead and take a moment. What's that difference between kilo and centi? Well, that would be a factor of 5 difference. But are we getting bigger? Are we making a larger measurement or a smaller measurement by making this change? We are going down. So our measurements are getting smaller, and that means that our numbers should be getting bigger, and it should be getting bigger by 10 to the 5. So we can just take that number that we have out in front and multiply it by 10 to the 5, and boom, we have it in scientific notation, and we are done. In example 5, we are going from the base unit hertz to megahertz. A mega is 10 to the 6 larger than a hertz, and so that is our difference there, 10 to the 6. And we are measuring in a larger unit, so we're going to expect our number to go down. And how much is it going to go down by? Well, it's going to go down by a factor of 10 to the 6. Again, we can divide the original number by 10 to the 6, or we can multiply it by 10 to the negative 6. Hopefully seeing when we multiply it by 10 to the negative 6, we can just put our 10s together, and 10 to the 8 times 10 to the negative 6 is going to leave us with 10 to the 2. And again, you can answer the final answer as 300, which is exactly what it is, but all of these I'm just keeping in scientific notation. And now finally for example 6, we are at our base unit of volts, and we are going to measure in our smaller unit of millivolts. That is a factor of 3 difference, and we are measuring in a smaller quantity, so we expect our number to grow. It's going to grow by a factor of 10 to the 3, which is going to leave us with a final answer of 4.5 times 10 to the negative 2. All right, plenty more examples for you to go through. I really would recommend doing quite a few of these because often just practice makes perfect with this metric unit conversion. All right, moving on to part 3. Now, part 3, we have standard unit conversions. And so unlike the metric unit conversions where we can just use that power of 10 rule for everything, The United States uses standard units, and we have just for the last 200 years been refusing to change our ways, and we continue to measure things in arbitrary units of feet and pounds and miles. And so, because we need to understand SI units of meters and kilograms, and we need to be able to convert between our standards and our metric units. To do that requires conversion factors. You do not need to memorize this table up here of conversion factors. Anytime you need to do this, I will provide this table for you. But we need to know how to do it. So how do we do it? The best way, and do not fight me on this, the best way is to do it exactly as I'm going to show you here, and we're going to follow basically what is stoichiometry or dimensional analysis. It goes by several ways, but what we're going to be doing is just multiplying our units by the conversion factors in such a way that they cancel out and give us our final answer. So let's take that first example. If I have 5.2 inches and I want to go from inches to centimeters, we scan our table on our length side of this table. We're looking for inches. First thing I see with inches is 1 foot is 12 inches. Not exactly what I want. The only other unit with inches in there is 1 inch is 2.54 centimeters. Bingo, that's the one I want to use. Now I'm going to set up that exact conversion factor. 1 inch is 2.54 centimeters. I'm going to set that up as a fraction. Specifically so, inches is in the denominator, and then my intended result is in the numerator. Now, what I am doing is technically multiplying 5.2 inches by 1. Now, I'm multiplying by 1 because 2.54 centimeters and 1 inch is equivalent. Like, they are different units, but they are equal to the same thing. So I can divide them, and that is the same thing as just multiplying it by a factor of 1. But what the actual result of this is, I'm not actually multiplying by 1. We see I'm going to do 5.2 inches times 2.54 divided by 1, but that 1 just cancels out. But I'm going to get a new number, but a new number that is expressed in centimeters. And how I know my final unit is going to be centimeters is a very important step that we look to see what cancels when we set up this statement. When I multiply out, notice I have an inches in the numerator and I have an inches in the denominator, and those inches cancel out. Once you are sure that everything cancels out, go ahead and do our math. Our math here is just 5.2 times 2.54, and that gets a final answer of 13.21. Make sure we express our final unit as what we should have, which is centimeters. Let's see this again with a longer example. So what if I have 1.9 days and I want to take that and convert it into minutes? Well, again, I'm looking to start with days and then I want to go down to minutes. So the best first step to take would be turning days into hours. Once we turn days into hours, we can then that's again multiplying by 1. We can multiply by a 1 again. We can keep going with this path until we get to the intended result. So we see that days cancels because I have I have a day in the numerator and a day in the denominator. We also see that hours cancels, 1 in the numerator and 1 in the denominator. Again, guys, take this step of crossing these out because it's the best way to ensure at the end, once I do this math, as long as I do the math correctly, we're going to be left with minutes, which is what we want to convert this to. And to turn 1.9 days into minutes, I'm going to take 1.9, I'm going to multiply by 24, then I'm going to multiply by 60. I'm going to get a final answer of 2,736 minutes. That's how many minutes are in 1.9 days. In example 3, we are going to introduce some units that are rates. So a rate is any one unit over another unit. We see our rate here is 60 meters per second, and I want to turn that into another unit for speed, miles per hour. Well, we set this up the exact same way. And the thing with rates is just focus on one thing at a time. I think the most common mistake that I see is that people want to try to do the meters and the seconds at the same time. We can only focus on one thing at a time. So what I mean by that is we're going to focus on just the meters first, and let's get meters to miles. And we have a conversion factor for that. 1 meter is 1609, or 1 mile is 1609 meters. Make sure we're putting the right numbers in the right spots. And then what I mean by that is meters has to be in the denominator so it cancels out, and the 1609 has to go with the meter. The 1 has to go with the mile. So doing just that, if I would stop here, my final result would be miles per second. But I don't want miles per second, I want miles per hour. So now that I'm done focusing on the distance, now it's time to focus on the time. And so for the time units, we need to make sure that we're going to go 60 seconds to minutes. We're also going to go minutes to hours to get what we want. But notice the very important factor that I just did here, which is I put 60 seconds in the numerator and 1 minute in the denominator. How did I know how to do that? Especially if we look at like the last one, we might not have done it the exact same way. Was because seconds starts in the denominator. So to cancel that out, I need to make sure my next seconds that's canceling with it goes in the numerator. Again, we're going to do the exact same thing with the minutes to the hours here. And the last step should always be, let's make sure that all of our units are in the right spots and they will actually cancel out. Meters in the numerator and the denominator, a second in the numerator and the denominator, and minutes in the numerator and denominator. The only units that don't cancel out are miles in the numerator and seconds in the denominator. Now we just go ahead and do our math. You are welcome to just multiply across. We would multiply across everything in the numerator, multiply across everything in the denominator, and then just divide. You can do it in each step. So if you want to do it 60 and then times 1 over 1609, that's fine too. Times 60 over 1 times 60 over 1, that's fine too. Really what we're going to end up doing is 60 times 60 times 60, all divided by 1609. Make sure we get our correct result of 134. That is in units of miles per hour, and that is the end of that unit conversion. All right, bit of practice really makes perfect with these standard unit conversions. And let's make sure we know how to do this last kind of problem, which is a rate, but it is a rate with a squared quantity in it. So now I have the measurement 23 pounds per inch squared. So units can often be squared. So in this case, a squared distance unit is just a measurement of area. So we're trying to conceptualize this unit. We're talking about like how much mass we have spread out over an area. And in this case, it's 23 pounds of mass per every square inch of area, which is a pretty highly dense object if you think about it. Now, not all of our units will be able to conceptualize. Some of them will be very obscure, and that's fine. You don't need to conceptualize them to be able to do this unit conversion. Just like the last time, focus on one thing at a time. The first thing I'm going to focus on is doing pounds to grams. And we looked at our conversion table chart, see if we have that conversion straight, and we do. We can go right from pounds to grams because 1 pound is 454 grams. And if I were to stop right there, I would have grams per inch squared as my final answer. But I don't want inches squared, I want centimeters squared. And so the way we do this case is kind of like the last one where I'm really looking at inches to centimeters, and I know that conversion. Because inch squared is in the denominator, I'm going to want to put my inches in the numerator and my centimeters in the denominator so it cancels out correctly. But we can't stop just here because I don't want to convert from inches to centimeters. I want to convert from inches squared to centimeters squared. Now, how can I do that? Because that conversion is not given on the table, but it's actually really easy because I can just square the conversion factor between them. What do I mean by that? I mean, I'm literally going to square the 1 inch over 2.54 centimeters. I'm going to square all of that. Now, when we're squaring everything in there, everything gets a square next to it. So if I'm distributing that power of 2, that's going to look like 1 gets squared, the inch gets squared, the 2.54 gets squared, and the centimeter gets squared. Now, in terms of our numbers, only that 2.54 being squared really matters because 1 squared is just 1. But now my units are correct after I distributed those squares, and I can now start canceling things out. Again, 1 pound, I have a pound in the numerator and a pound in the denominator. And I also have an inch squared in the denominator and an inch squared in the numerator. Once we do that math, we're sure that we're going to have leftover grams per centimeter squared. Now we go ahead and do it. That's going to be 23 times 454 divided by 2.54 squared. And our final answer is 1,619 grams per centimeter squared. All right, that is it for part 3. Now moving on to part 4. Now, in part 4, we're going to go over everybody's favorite exponent properties. Now, will you see exponents like this specifically throughout the use of AP Physics? No. You're not going to get these crazy messy exponent problems and be asked to simplify them. But it's still really important that we understand these exponent properties, we really have them internalized, because it makes everything so much easier when we are rearranging equations. We understand how these exponents can go together by knowing what these rules are and how we just can combine or subtract or bring together or distribute all of these exponents. Okay, so we have these rules up in the corner there. Go ahead and make sure we understand those, but the best way to see it is just by example. So let's see example 1. In example 1, we have x to the 4th, x to the 3rd, and x to the 0. Well, x to the 0, or I'm sorry, y to the 0, anything that's raised to the 0 power is just equal to the 1. Now, it does have the caveat that we can't, if y was 0, 0 to the 0th power is not 1, but we're going to assume that none of our exponents are 0 for the remainder of this problem to make it nice and easy for us. So that y to the 0 just becomes 1, and now we're multiplying everything by 1, so that can really just go away. Now x to the 4th times x to the 3rd, well, we can just follow the product rule. We have the same base, and so when we're multiplying two exponents that have the same base, we can just add those exponents together. So x to the 4th times x to the 3rd gives us x to the 7, because 4 plus 3 equals 7. Now, in example 2, we have x to the 3rd, y to the negative 2, both raised to the 2nd power. When we have powers raised to a power, we call that the power. We can follow the power rule, and in that case, we multiply everything by the exponent that we were raising it to. So in the case of x to the 3rd, it's being raised to the 2nd power. Well, 3 times 2 is 6, giving us x to the 6th, and then y to the negative 2 gives us y to the negative 4. Now, technically, right now, this is perfectly fine to have negative exponents. Y to the negative 4th, there's really no reason that that's any better than a positive exponent, but we're going to follow the conventional way of doing things, which is going to be leaving all of our exponents getting all of our exponents to be positive. So how do I take a negative exponent and make it a positive exponent? Well, all negative exponents are just flipped. They're just inverses. And so the x to the negative 4 is really just 1 over y to the negative 4 is really just 1 over y to the 4. So we have x to the 6 times 1 over y to the 4, or it's just y to the 4 in the denominator. And that is our nice, pretty way of bringing these both together. Now in example 3, we also can follow the power rule that 6 on the outside gets multiplied to everything on the inside. Both the c to the 8's going to get multiplied by 6, the b to the negative 5 is going to get multiplied by 6, and what's often forgotten is the 2 out in front that doesn't have an exponent is also going to get raised to the 6th power. Now, if we don't have an exponent, like on the negative 2, really, we're raising that negative 2 to the 1st power, because anything raised to the 1st power is just itself. So 1 times 6 gives us negative 2 to the 6th power, and then the b to the negative 5 becomes b to the negative 30 when we multiply by 6, and the c to the 8 becomes c to the 48 when we multiply that 8 times 6. Now, next thing, we just need to get rid of any of these negative exponents, and while we're at it, let's go ahead and make this negative 2 to the 6th an actual number. And we can do that when anytime we actually have values. Let's just go ahead and put them in whole number rather than leave them in exponent form. So negative 2 to the 6th power is going to give us positive 64. The c to the 48 doesn't change at all. And then that b to the negative 30, we just need to go ahead and inverse that and put that in the denominator, giving us our final answer shown there. Next, in example 4, seeing that we're also going to follow the power rule, so that negative 3 gets distributed to everything. 3 to the negative 3, g to the positive 15, and then t to the negative 24. Now, again, last step will just be to let's go ahead and raise 3 to the negative 3rd power. Well, that's the same as 1 over 3 to the 3rd power. And then likewise, t to the negative 24th power is the same as 1 over t to the 24th power. 3 to the 3rd power is 27, and then so we simplify to the answer shown there. Next, in example 5, we have lots of exponents here, and now we're going to follow our quotient rule. which is when we have exponents that are being divided by each other, we can just subtract those exponents when they have the same base. So starting with my f to the 5 in the numerator, well, the f to the 2 in the denominator, we can cancel those two bases out, or we can cancel out some of the exponents and be left with f to the 3. The d to the negative 8 minus 2 would be d to the negative 10. The z to the 3 minus z to the 5 will become z to the negative 2, and then nothing cancels or mixes with that y to the negative 3 that we had in the denominator. Last step will just be to flip them and put them in the right spots. If we have a negative exponent in the numerator, it goes to the denominator. If we have a negative exponent in the denominator, it goes to the numerator. So our final answer, f to the 3, y to the 3, over d to the 10, z to the 2. And lastly, for example 6, now we see we have a to the 5, d to the second. Those are both being raised to the second power. And then in the denominator, a times d to the 3, both being raised to the third power. And then everything is being raised to the second power. So what we're going to do here is just follow the power rule twice. And let's start on the outside and work our way in. So instead of multiplying, or what I'm really going to do is just distribute down that 2 to the 2 and the 3 that were there to now raise my numerator to the 4th power and raise my denominator to the 6th power. And now I can distribute the powers that are on the outside, giving me a to the 20, d to the 8 on the numerator, and then a to the 6, d to the 18 in the denominator. Last step will be to cancel out using the quotient rule. So a to the 20 minus a to the 6 gives me a to the 14, and in my denominator, or I could do in my numerator, d to the 8 minus d to the 18 would give me d to the negative 10, which gets sent down to the denominator to make it a positive exponent, giving the final answer shown there. All right, exponents, they can be tricky, but again, practice makes perfect with these. I really want to make sure that we have a good grasp on exponents, and we're just not scared of these exponents. We're feeling free to combine them, to simplify, because when we know how to simplify, it makes things simpler. So make sure we practice this, and now let's move on to part 5. In part 5, we are doing operations with scientific notation. So this is my first 1-star section of our AP summer assignment. And I 1-starred this not because it's not useful, just because you will always have a calculator on hand to be able to do this with. But I'd like to just point out to you how knowing the exponent rules can just make things go a lot quicker for us. And hopefully, we're going to see a lot of numbers in scientific notation, and that doesn't always mean that we automatically need to get out a calculator because you're seeing a 10 to some power here. Actually, things are a lot quicker when we don't use a calculator for a lot of these examples. Now again, at the end of the day, you are always going to be able to use a calculator, but for this part, go ahead and try it without a calculator to see if you can pick up what I'm putting down. So in example 1, if I have 5 to the 4th, times 2 to the 5th, well, the commutative property of multiplication tells us we can multiply these in any order because we're just multiplying everything together. So let's go ahead and do 5 times 2 first, and that would give me 10. Now we can also do 10 to the 4th times 10 to the 5th, and from what we just covered in part 4 with exponent properties, they have the same base, so we can follow the product rule and add those exponents together with a like base. That simplifies this times to 10 times 10 to the 9. Well, if we're multiplying 10 to the 9 by just one more power of 10, that is, or we could think about it as 10 to the 1, we are just going to get 10 to the 10 as our final answer. Now again, once we do this real quick, that's a lot quicker than just pulling out a calculator and seeing that. See this again for example 2. Now I have 1.5 times 10 to the 4 times 2 times 10 to the negative 3. 1.5 and 2 come together to give us 3. 10 to the 4 and 10 to the negative 3 come together to give us just 10 to the 1, which is just 10. So what's 3 times 10 to the 1, or 3 times 10, would just be 30. Again, real quick, it would have taken a lot more time to type all of that into a calculator than just to use our exponent rules here. With example 3, we have a 1/2 in front, 9, 10 to the negative 2, 6 times 10 to the negative 5. We're seeing, of course, I want to put those 10s together and get 10 to the negative 7. I can go ahead and do 9 times 6, But what am I going to do with that 1/2? Well, rather than doing 1/2 times 9, which is going to give me a 4.5, let's go ahead and do 1/2 times 6, because then that simplifies it down to an easy 3. And then I can do 9 times 3, which I know right off the top of my head is 27. Now I have 27 times 10 to the negative 7, which I could leave it as that answer right there, or go ahead and put it in proper scientific notation, which is going to be 2.7 times 10 to the negative 6. In example 4, we have a square root here. So don't let the square root scare you. When we are square rooting anything, we're really just raising that thing to the 1/2 power. So we can think about it like that, or we can go ahead and try to simplify what we have under this radical to try to get ourselves a nice value here. So square rooting a fraction means we're really just square rooting everything under that fraction, and we can look at that all separately. So again, all of these square root symbols are really just raising what's under them to the 1/2 power. So 2 to the 1/2 power isn't really that helpful, but 10 to the 10 to the 1/2 power is really just going to be 10 to the 5. For the square root of 4, we know is going to be 2, and the square root of 6, again, that's 6 to the 1/2 power. It's just going to be half of 6, which is just going to be 3. So now I can't simplify that square root of 2 any further, and I can't combine square root of 2 over 2. Like, that is as simple as it gets. We could make this a decimal answer, but that defeats the purpose of trying to do this all without a calculator. And a math teacher would always prefer you to leave the radical as a radical, because then that's the whole number answer rather than the decimal. But we can go ahead and simplify that 10 to the 5 and 10 to the 3 to give us 10 to the 2, and we're just going to leave that square root of 2 over 2 uncanceled out in front. And now that's a simple way to that's a quick way to simplify this problem. In example 5, we're raising that numerator to the second power. So that 4 is raised to the second power, that 7 is raised to the second power to make it 14, and then the 2 to the 6 is left undisturbed. Let's go ahead and do 4 to the second power is 16, and everything else stays the same. I can now go ahead and do 16 over 2 to make that 8, and I can go ahead and use my quotient rule to do 10 to the 14 over 10 to the 6. 14 minus 6 gives me 8, so my final answer is going to be an 8 out in front, times 10 to the 8. And then lastly, for example 6, we're going to do that same process of power rule up in the numerator to give me 4 squared and 10 to the 5 squared to give me 10 to the 10. And then my denominator, I'm going to go ahead and do 2 times 2 to get 4, and going to go ahead and get 10 to the 6 times 10 to the negative 3 to get 10 to the 3. Now we simplify this a little bit more. 4 squared gives me 16, but divided by 4 drops me right back down to 4. And then 10 to the 10 over 10 to the 3 gives me 10 to the 7. So final answer, 4 times 10 to the 7. All right, hopefully you pick up on this. And again, not the most important one that we have mastered here, but some fun practice and a good implementation of exponent rules in scientific notation, which we will come across all throughout the course. Moving on to part 6. Part 6 is our first 5-star section, one of the most important parts that we need to have mastered. In this section, we are rearranging equations. So we are essentially just solving equations for the indicated variable. And you will be doing this over and over and over again all throughout the course. Physics is a very equation-heavy and very math-heavy science, if we haven't figured that out already, but a lot of that is based on you just fundamentally understanding how our quantities related to each other. And the way we truly understand that is not just by getting an equation, but being able to relate then in an equation, how is K affected by V? How is K affected by M? How is X affected by T? And we understand that relationship by rearranging equations to solve for certain quantities. So let's do this in example 1. We see we have K equals 1/2 mv squared. We want to solve this for M. So on all equations, we can just follow equations rules. We can do whatever we want as long as we do it to both sides of the equation. If I want to start by getting M by itself, I want to move that 1/2 to the other side, and I do that by multiplying both sides by 2. Multiplying the left by 2 gives me 2k, and multiplying the right by 2 cancels that 1/2, leaving me with just mb squared. Now again, I want to get m by itself, so the next step is going to be to move the v squared to the other side. Since we're multiplying the m and the v squared, I'm going to divide both sides by mv squared. That cancels it on the right and leaves me on the left 2k over v squared. Then it's just standard practice to rewrite the equation with the variable we want to find on the left all by itself equals everything else all on the right. Next, we want to solve this for v. We can go back to the initial equation to do that. If we're confident in our answer for the first one, we can go off of that answer. If I'm going off the answer that I have here, the first thing I want to do to solve this for v is get v out of the denominator, because I can't solve for v, can't move the 2k over to the other side and have 1 over v squared in the denominator. We need that v out of we need the v squared out of the denominator. So getting the v squared out of the denominator moves it to the other side. We then divide both sides by m. We should end up with 2k over m is equal to v squared. Then whenever we have an equation, we're almost done, we want to equal v to v, not what v squared is. So we need to undo that square by square rooting both sides, giving me a final answer. V is equal to the square root of 2k over m. Let's try this in a little bit more complex of an equation. In example 2, TP, that T and the P are connected together, that P is a subscript, equals 2 pi times the square root of L over G. Solve this for L. So to solve it for L, we got to get rid of this square root. If L is trapped right now under the square roots, then we need to get rid of that square root. We can get rid of that square root by squaring both sides, but squaring both sides squares everything. Oh, I guess I'm going to go ahead and move the 2 pi over to the other side, and then I want to square both sides. But again, squaring both sides squares everything. So that TP is going to get squared, the 2 is going to get squared, and the pi is going to get squared. And then the L over G is all by itself over on the other side. Notice my 2 turned into a 4 because 2 squared is 4. And I think a common mistake I see in these is forgetting to square the pi. But the pi needs to be squared as well because everything on the left was getting squared. Now the last step is to solve this for L, and we solve this for L by moving G to the other side. So my final answer is going to be TP squared times G over 4 pi squared. And that is how I solve that for L. Now the easiest way to solve for G is just to go off of my last problem. And now if you notice, I already have G. I have this solved for L, but G is in the numerator on the right-hand side. So I need to move the 4 pi squared over. So I'm going to multiply both sides to do that. Now on the left, I have 4 pi squared L. And now I need to move that TP squared to the other side through division. So my final answer for G, 4 pi squared L in the numerator, divided by TP squared in the denominator. And those are both our final answers for example 2. Now, surprisingly, the worst equations to have to solve are when we have multiple terms. So what do we mean by term? It's just when we have different things separated by either plus signs or minus signs. So in example 3, the Q is a term, the 5b squared is a term, and then the minus beta over z is its own term. And that b and that beta are different things here. So if the first thing I want to do is solve this for z, we need to get z all by itself. So in effort to do this, I'm going to subtract both sides by 5b squared to move that 5b squared to the other side. I then notice that we have this negative sign. We have negative b beta over z on my right hand side. Let's go ahead and get rid of that negative sign by just multiplying everything by -1. And every term needs to be multiplied by -1. So that means the q becomes negative, the 5b squared becomes positive, and then the minus beta over z also becomes positive. And that just helps me get z by itself. Again, trying to get z by itself, we can't solve for something when it is in the denominator. So I don't want to move the beta to the other side. I want to move the z to the other side to get it out of the denominator. Now I'm going to be multiplying both of those terms by z. So I put it like this, and you can think, oh, and then distribute. Well, that's not what we want to do yet. We don't want to distribute that z. We could, but that's not going to help us solve this for z. But both things would be being multiplied by z. But what I want to do is now get z by itself. So what I want to do is now divide. I'm going to divide by everything in those parentheses. And so what that final answer is going to yield is going to be a beta in the top. Then all that beta is divided by all in the denominator, negative q plus 5b squared. And that's my final answer, solved for Z. Now let's go ahead and solve for B. I'm going to go ahead and go back to my original equation to do this. To solve this for B, we want to get the B by itself. So I'm going to add that beta over Z term to the other side. Now I have a 5B squared. This is where we'll see a lot of people go wrong because it's really easy to make a mistake in this next step. So to get B by itself, we have to divide both sides by that 5. Well, dividing both sides by the 5 means both terms are being divided by 5. And we could put it like this, but I'm going to always encourage you never to use improper fractions because it just gets very confusing very quickly. So rather than writing it like this, just think about both terms are being divided by 5. So for the Q, that's just Q over 5. And then for the beta over Z, if I divide that by 5, that 5 is just going down in the denominator. Now I have a 5 distributed rather than like out on the outside. And that's just a lot easier for us to process and look at, not nearly as ugly as that improper fraction. But now that I have that correctly distributed, now I want to solve this for B, and my last step will be to take the square root of both sides to get B all by itself, giving me a final answer that B is equal to the square root of the quantity Q over 5 plus the quantity beta over 5Z. That's my final answer. Like I said, those subtractions, when we have multiple terms, it can get pretty dicey, but just follow your algebra rules. We're multiplying, we're dividing, we're adding, we're subtracting. As long as you're being mathematically consistent, you really can't go wrong here. You just got to follow the right math rules to get that whatever letter all by itself. All right, moving on to part 7. In part 7, this will likely be brand new to you, this idea of dimensional analysis. Now, dimensional analysis is another 5-star because we will be dealing with not only a lot of equations that we need to rearrange, but we're not often sure where these equations come from. You're going to be given a ton of equations where you have no idea who came up with this. Sometimes it'll be you, or it'll be your classmates coming up with equations. Sometimes it'll be me. And then at the end of the day, you're going to have AP exams where they're just going to give you equations and ask you this question of, does this equation look right to you? Could this be a true equation? Is this equation valid? And how we determine if an equation is valid is by looking at the units. Would these units make sense? Now, we're going to, throughout this course, measure a lot of different things. And the main things that we're going to measure are listed in this table here, length through momentum. It's not important that we understand fully what these dimensions are, but we understand that they are measured in certain ways and they have what we call SI units. Now, when we have an equation, the units need to be the same on both sides. And so when we are doing dimensional analysis, we are just checking to see, are the units on the left side the same as the units on the right side? So let's see how we would do that for example 1. We see we have P all by itself. Well, the units for momentum, P, are kilograms times meters per second. So that is one thing on the left side. Now, on my right side, I have 3 different things. I have mass, which its units are kilograms. I have velocity, which its units are meters per second. Then I have length, which has the units of meters. Are these the same thing? Well, as I always say, the improper fractions never make this easy for us, so let's not make this improper. Let's see, how would I cancel that? Well, that cancels out on the left-hand side to give us just kilograms. The meters are getting canceled, so I have just kilograms per second on the right-hand side, which we see is not the same thing as what we have on the left-hand side, which is kilograms times meters per second. So these are not the same thing, so we would just answer this question that this equation is not valid. There's no way that this could be true because it does not correctly relate it couldn't correctly relate these quantities if the units are not matching up to make sense of that. All right, let's see how we would do this again in example 2. So I'm going to start with my kilograms mass, or start with my mass, which is in kilograms. The momentum per mass is being squared. Let's take it out in steps. momentum P is kilograms times meters per second. That's getting divided by kilograms. And then notice on both sides of my bracket, or on the right-hand side of that bracket there, it's being raised to the second power. Then on my right-hand side, I have my units for acceleration, my units for mass, and my units for distance. Now, let's go ahead and simplify this down a little bit. So one way this simplifies down is the kilograms and kilograms on the left side are canceling out. The 1 kilogram by itself is staying the same, but the kilograms over kilograms cancels out. And now I have meters per second being squared. Then on my right-hand side, I didn't do anything different. Now on that left-hand side again, if that meters per second unit is getting squared, that's going to be kilograms times meters squared per second squared. Now that I start to bring together the terms on my right-hand side, we see the kilograms just stays kilograms, the second squared just stays second squared, but I have 2 meter units, which I can go ahead and bring together to make meters squared. Now notice, as we work through here, everything just worked out, that we have the same thing on both sides of these equations. And that's all we're trying to figure out is, do we have the same units? If we do, then it is a potentially valid equation. All right, and the last kind of problem we're going to see with this dimensional analysis is solve for this constant, and the constant will always be labeled C. We're going to solve for what the units of C need to be to make this equation valid. So I have this complex equation here. We can make the units of C anything. We were just asking, what do the units of C need to be to make this equation make sense, to make it a potentially valid equation? So how do we do this? So what we need to do is just solve this equation for C. So let's go ahead and practice our equation solving to get C all by itself here. Well, solving that for C is going to be multiply both sides by 4t, divide both sides by ma squared, and we're going to get what we have over here. And then can we simplify this at all? If we can, simplify it. If you notice, we have a t in the numerator and a t in the denominator. So let's just get rid of those t's. They cancel out, leaving us with our final equation solved for C, 4e over m squared a squared. Now, all I need to do is plug in what the units are for all of these things, simplify them, and then now I'm going to know what the units of C need to be to make this equation be valid. So how do I plug in for the units of everything? Well, let's first start with 4. What are the units of 4? Well, 4 is just a number here, and a lot of equations just have numbers in them. A number is just relating, like it's just telling us about the size of things, like something might be twice as big, we might need to take only half of this value. Numbers themselves do not have units. So starting with E, the units for E are showed there through energy. We're dividing by a mass squared and dividing that by a acceleration squared. Now this is a nice, ugly, improper fraction that I'm sure you might see and be like, there's no way I'm going to simplify this. And you can. Let me show you how easy it is to simplify these things when we have fractions being divided by fractions being divided by fractions. Okay, start with whatever we have on the numerator and put it all together. So in this case, I'm going to start with E, which is just kilograms times meters squared per second squared. Notice that E did not change at all. Now, I'm going to multiply by the reciprocal of each thing in the denominator. What do I mean by reciprocal? I mean the inverse. I mean, that's a property of division, right? That instead of dividing, if I want to divide by 2, I could multiply by its reciprocal, which is 1/2. We can do that same thing with these units here. So rather than taking this and dividing by kilograms squared, let's multiply it by 1 over kilograms squared. We're going to do the same thing with meters per second squared, which is being raised to the second power. So notice that becomes meters squared per second to the 4th. But I'm going to multiply by the reciprocal. So the seconds to the 4th goes in the numerator and the meter squared goes in the denominator. And now we can just multiply right across. So the property of fraction multiplication, multiply anything, just multiply the numerator all together and multiply all of those denominators together. So what that's going to give me in my final numerator is going to be kilograms times meter squared times seconds to the 4th power. And in my denominator, that's going to be seconds squared times kilograms squared times meter squared. Now things then start to cancel once we do that. And my final answer is going to be seconds to the 2nd power divided by kilograms. So that is what C needs to be in our initial equation to make this equation dimensionally consistent. Right? Best of luck as you go through the dimensional analysis section. I promise you can do this, but practice always makes perfect. Moving on to part 8. Part 8 is going to be a quick part here. We are going to go over the rules of Sig Figs. So if you've taken another AP Science class, or maybe just a regular science class, you likely may have heard of significant figures. Significant figures, I think, are important for all sciences. But AP Physics does not heavily enforce the use of it. You're not going to see many questions that's like, how many sig figs are in here? They don't require you to correctly round the correct number of sig figs when you're doing sig math with certain values. But I think it's important for us to learn for one big reason, and that is this is a science class and not a math class. And I understand your frustration with that when this assignment is literally nothing but math review. But what we are doing in this class is math, but we're doing math with actual values, with the numbers that came from the real world. And whenever a number comes from the real world, there is always uncertainty in it. We can never be 100% accurate about anything we measure. Take the length of something. You say something is 2.5 inches. Well, is it 2.5 or is it 2.498? Is it 2.498 or is it 2.498,127? You can always be more and more accurate. And then there is a limit to how accurate we can be about anything. So in any measurement you ever see, it has a built-in amount of how accurate were they being when they measured. Now, what I need you to do is just take a look at these numbers. Tell me how accurate they were being, aka how many significant figures are there, and then how can we dumb this number down to make it less accurate while still retaining the essence of what that value was. Okay, let's start this with number 1. We see we have the number 15,300. Well, it tells us in our sig fig rules that trailing 0, so all the 1, the 5, and the 3 are all non-zero, so they have to be significant. So this is really just a question of figuring out, is this 0 important or not? It tells us trailing zeros are only significant if there's a decimal point. There's no decimal point in this number, so only the 1, the 5, and the 3 are significant, so this number has 3 sig figs. How would I take this number, and I want to make the same number just less accurate? So I couldn't make this number like 15, because that would be entirely different than 15,300. Now I want to lose a sig fig, but I don't want to lose the size of this number. So the number 15,000 is about the same. It's just a little bit less accurate than our original number. And that's the key to as we're rounding this down. So we've done both steps to this part, which is how many sig figs were in the initial number, and then round it down to the indicated number. All right, in example 2, you might ask yourself, well, what if we actually measure something be perfect and we have all these zeros and we measured them? How do we show that? Well, if I measure something to be exactly 8,200 meters, then I would show that by putting an unnecessary decimal point in the number. So now the 8 significant, the 2 significant. Are these zeros significant? Yes, because they're trailing and there is a decimal point in the number. So this is how we go out of our way to say, we're not just estimating it's about 8,200, 8,200. It is exactly 8,200. So how would I round this down to only one significant figure, though? Well, again, this word about, I think, is really helpful. How do I make this, and I just want to be less accurate with what I'm saying? Well, you are saying that this is exactly 8,200 meters. I'm going to say it's about 8,000 meters. It retains the same essence, but I'm just being less accurate with what I'm saying. Significantly less accurate because I'm losing 3 whole digits of significance by rounding it down to just one sig fig. In example 2, see we have some leading zeros here, 0.00. Leading zeros are never significant. The zeros in between non-zeros are, so that 5, of course, is significant. The 0 in between the 5 and the 8 is significant. And is that last, of course, the 8 is significant, but is that last 0 significant? Yes, because it's trailing, and there is a decimal point in the number. So the 5080, all of those are significant, and I want to round this down to 2 sig figs. Well, again, the numbers in front are never significant, so I still want to keep the 0.00. I'm going to keep about the same estimated size of this. I now just want to drop this down to be less accurate. So I'm going to have 0.00, then a 5, and then I'm just going to decide, am I going to round this next number, or am I going to keep the next number, or am I going to round it up? We're just following rounding rules for that. So after the 5, my next number is a 0. Well, after that 0 is an 8, so that 8's going to round that 5 up. And so now I'm going to round it to 0.0051. Essentially the same number, just a little bit less accurate. Now for example, now for the fourth one, we have the number 1,584,680,000 grams. And now I want to take this number. Well, first I want to know how many sig figs are in here. Well, all of those numbers in front are non-zeros. So are those last 4 zeros significant or not? No. They are trailing zeros, and there's no decimal in here. So the 1, 5, 8, 4, 6, 8 are all significant. How would I round this down to 4 sig figs? I'm going to keep all of those numbers in the front, and then I'm going to keep the 1, keep the 5, keep the 8, and then at the 4, I'm deciding, do I keep this 4 or am I going to round it? Of course, we round that 4 to a 5. So now I'm just being the same value of number, a little bit less accurate, that only has 4 sig figs in it. All right, the easy rule with sig figs is that by putting a number in scientific notation, you can really easily determine how many sig figs are in a number. So for the next 4 examples, I'm going to put my final answer in scientific notation. So for the number 95 billion, and then 95 billion, notice there is a decimal point at the end there. So somebody is going out of their way to say this measurement they made of volume is exactly 95 billion. So because that decimal point is there, all of those trailing zeros become significant. So initially, this value has 11 significant figures. I want to take this value with 11 sig figs and just round it down to 1 sig fig. Well, how could I possibly do that? Well, I just want to keep the 9, but we always, at the one number we're keeping, we look at the next one and ask, do we round up or do we stay the same? Well, that 9's then going to round up to a 10. Well, the way to think about that is we really had 9 times 10 to the 10, or I'm going to round that up to be 10 times 10 to the 10, which becomes 10 to the 11 liters. Right, again, the number out in front, and when we put a number in sig figs, how many digits we have in front tells us the number of sig figs. In that value, 1 times 10 to the 11, there's only one number out in front, so there's only one significant digit. You could ask yourself, couldn't I just write that as 10 to the 11, not 1 times 10 to the 11? Sure, we can write it as just 10 to the 11, but I was just making the point for the sig figs here. For the next one, we have this number. The zeros in front are not significant, but that final 0 at the end is, because there is a decimal portion. So that is 7 significant figures, and I want to round this down to 1. We want to keep the 0.00. We want to keep the 5, and then we're asking ourselves, does the 5 stay the same, or does it round up to a 6? In this case, it's going to round up to a 6. So we could have the number 0.006, or we could write this in scientific notation as 6 times 10 to the negative 3, because those zeros out in front, that's what we mean by they're not significant. They are only holding the place. And know what else can hold the place? The 10 to some power can also be our placeholder. In our next example, we have another decimal point. We see the first 3 zeros are not significant, and then all the other zeros are in between non-zeros, so they are significant. So we have 7 significant figures here. We want to round this down to 2. The 0.00 just stays there. We keep the 9, and then we're wondering, do we keep the next number or do we round it up or down? We're going to keep the 0. So we're going to keep the 9. We're going to keep the 0 because it doesn't round up. So I now have the number 0.0090, or in scientific notation, 9.0 times 10 to the negative 3. Now notice I'm going out of my way to write 9.0, not just 9 times 10 to the negative 3, but 9.0 times 10 to the negative 3. That is communicating that the 9 is significant and the 0 is significant. And so this value then has only 2 sig figs in it. All right, lastly, for our last example, you're going to see an example of where you have to keep a number. We would have to put this in scientific notation to round it down to this many sig figs. So every zero in this number is significant because all of the zeros in the middle are between non-zeros, and then that 8 at the end, there's a decimal, so that trailing zero is significant. So this is 4, all digits, or 12 digits, all of them are significant. But to round this down to 4 would mean we would want to keep the 8, keep the 4, keep the first 0, and then keep the second 0. But then how could I keep the first 0 and the second 0, but not keep the last 0, but still make this significant? So like we could write 8400, but I need only those 4 zeros, but not that last 0 to be significant. The only way that we can do this is by putting this number in scientific notation, to put it as 8.400 times 10 to the 4. Now the value of this is what we need it to be, which is essentially 84,000, but we want to say only those first 2 zeros. Like we know for sure those first 2 zeros are 0, but maybe we're not so sure about that last 0. And that's how we would do that. So again, converting to scientific notation is an easy way to do this. You're welcome to keep all answers in scientific notation for this page. You can leave them as regular values. It's really up to you. But happy sig fig hunting for the rest of this part. Now let's move on to part 8. Now in part 9, we are doing some operations with sig figs. And again, this is another 1-star problem because AP Physics does not force you to follow these rules. But again, just to understand that these are units and they do have certain rules, I think it's helped you appreciate the science that we are doing here. So let's learn what these rules are. So if we are adding or subtracting, our rule is to the first rule is always do the math. So like whenever we're given a problem, we want to use a calculator. We want to plug these numbers in. We want to do the math that it tells us to do. But what we are doing here is rounding this to make our answer a little bit less exact. Now, when we are doing this for addition and subtraction, we just need to worry about the decimal places of our numbers. And so if I have 3.87 meters plus 984 meters minus 2.9 meters, it's weird that we're adding these measurements and they're not all to the same number of decimal places. Now we can go ahead and do this math, and that should always be the first step. We put this into a calculator. The calculator spits out the answer 984.97. But what's weird is that especially that 984 didn't have any decimal places in it. While the first number went to 2 decimal places and the last number went to 1 decimal place. So like, is there decimal places after that 984? Was it exactly 00? If it was exactly, like, the person did not put 0.00 to communicate that. And so how we deal with that uncertainty, that questioning of like, is there more after that 984, is we just round this number and we round it to the least number of decimal places of our measurements. And so for that case, that's going to be the 984 has no decimal places. And so our final answer needs to go to no decimal places. And so we round 984.97 to have 0 decimal places. And so that means we round that 4 up to a 5. And our final answer is going to be 985. Again, all we are doing is making our answer a little bit less accurate to account for uncertainty, which is a very important thing. If imagine we are measuring the dimensions of an airplane and everything needs to be exact, like it's very important that we understand that the measurements have uncertainty, and some measurements have more uncertainty than others. And we are limited by, when we're putting numbers together, you're always limited by your most uncertain value, like in getting what your final answer is. All right, so for addition and subtraction, all we got to do is worry about the decimal places. For multiplication and division, though, we round based on sig figs. And just like the other ones, we always do the math first. So in your calculator, what's 15,300 times 2.1? Well, that calculator gives you an answer of 32,130. But we are going to round this answer based on our lowest number of sig figs. Well, the number 15,300 has 3 sig figs. The number 2.1 has 2 sig figs. So my final answer needs to only have 2 sig figs. So the answer I have written down there has 4. So how do I take this down to 2? Well, I keep the 3 and then I keep the 2 because that 2 does not get rounded up by the 1. So my final answer is 32,000 milliliters. That should be milliliters squared since I am multiplying 2 milliliters together. All right, again, in the third one, we are multiplying two numbers and then we are dividing it by another number. Do the math. So in our calculator, we do 9.5 times 10.4, and then we're going to divide that answer by 0.06. Gives me the quantity, 16,400, and then 0.6 repeating. So this is where it's very important that we don't say that we know to this intense accuracy. That's what this final answer is. Mathematically, yeah, that's what that answer is. But we're taking a number with only 2 sig figs, times a number with 3 sig figs, dividing a number with only one significant figure. That number 0.06 is not a very certain number. That has a lot of error in it by only having one significant figure. Yet we're going to report out that we know to 12 or 14 significant figures that this is a final answer. There's no way. We have to account for this uncertainty by rounding our answer down. And we would round this answer to only 1 sig fig. Now in this case, that's going to round it quite a bit. How do I round this to 1 sig fig? We want to keep the 1, and then we round that 1 up to a 2, and then we keep the other, we change all those other numbers to 0 to keep the place value. That's going to give us an answer of 2,000 kilograms times meters per second. Now that was a big round. And I think where a lot of you get frustrated is we look at this number and we're like, why are we making things less accurate? Well, it's better to lower your accuracy to account for uncertainty than to try to say like you know for sure that that's what this measurement is. Now in this case, we are jumping quite a bit, but that's because we are limited a lot by our one significant figure in that time measurement. And so we end up having to round that answer a lot. So when it comes to actually doing this, I'm not expecting you to practice this, but you'll notice that I will continue to round answers throughout the rest of this assignment and throughout the class. I'm going to round answers quite a bit, more than you might, because this is not math. I'm not going to always take it to 4 or 5 decimal places, whatever you were taught, because each one of those decimal places is an amount of certainty that I'm not ready to give if all of our numbers in the original statement only had 1 to 3 significant figures. All right, let's see this last example. And in this case, we have both addition and subtraction and division in here. Now, my rule of thumb for you is going to be only ever round once. So our first step for any of these problems should be do the math. And so do the math as it is stated. So we need to do 8.12 plus 9.688. Do that first. And then we're going to divide that by, in parentheses, 10.97 minus 1.8. So do the math. We only ever want to round once. We don't want to round numbers twice or 3. We don't want to round the numerator, round the denominator, and then round again for the multiplication and division. So do the math, and then we're going to round once. So then you ask, which rule are we going to follow? Are we going to follow the decimal rule, or are we going to follow the addition, subtraction rule, and the multiplication and division? In truth, follow both. But follow the one that makes you round more, if that makes sense. So if I follow my decimal rule, my lowest number of decimals is 1 decimal place. And if I follow my sig fig rules, my lowest number of sig figs is 2 sig figs. So in that case, we actually end up doing the same thing no matter what. And we're going to round this to 1.9, and that 9 then stays a 9 and doesn't get rounded up. So if we had a decimal place, if that 1.8 was instead 1.81, we're still only going to round it to 1.9. Well, I guess that rounds it, because then that would also make me have 3 sig figs. We're going to always round whichever one makes you round more. So whatever makes you drop it a little bit more. If we only had 1 sig fig, and we needed to keep this as just 1, then we would have rounded this number to 2 and not gone to any decimal places. Most likely, almost 9 out of 10 times, the thing that is going to make you round more is by following the sig fig rule, not following the decimal rule. So when in doubt, just follow the sig fig rule and don't worry about the number of decimal places. But always in any problem, do the math and then just round it one time, and you're just going to try to make the number less accurate to account for that uncertainty in these measurements. All right, that is part 9. Now let's move on to part 10. Now, parts 10, 11, 12, and 13 all have a common theme, and that theme is vectors. And vectors are going to be an extremely important part to AP Physics and just understanding physics in general. Now, a vector is any measurement that has both magnitude and direction, or both size and direction. So it's any measurement that has like an amount to it, but it also has direction to it. So think when I tell you how far you moved, like from one place to another, I moved 2 meters east. The 2 meters is how much it is, and the eastward is telling you what direction that motion took place. Many values in physics are vectors, and all vectors exist not only in just like forwards and backwards, that can be the direction, but also in a whole realm of directions. And so what we're seeing here are 2D vectors, vectors that we can move both forward, upwards and downwards and side to side, or we can move both north, south, east, and west. So we're going to see, how do we visualize what these vectors are? There's kind of a standard way to do it. So let's start with the first example where we have 40 meters, and this vector is 30 degrees north of the east line. Notice how that is said. It's not 30 degrees northeast, it's 30 degrees north of the east line. And so how we start all of our vectors is we're going to read this backwards. So we're going to start at east, because this is saying I want to go 30 degrees north of that east line. So notice my vector is starting east, and then I want to drag this vector northwards until we get an angle that is approximately 30 degrees. Now, you do not need to be perfect with this, but we should be trying to make this approximate. Like, notice I didn't drag this halfway. I didn't drag it all the way up. So if I drag it to make it completely north, that would have been 90 degrees. That's far too much. Like, I don't expect you to get out a protractor here, but I do expect you to kind of keep it in the realm of where we think that might be, which in this case, that's going to be less than half, but a little bit above. So that is about 30 degrees there. And then we just need to label. We need to label what is the length of this vector, it's 40 meters, and what is the angle that we made, and we measured that angle exactly like shown, where we are going north of that east line. Again, very important that we are starting at the second one and moving in the direction of the third one. Now, let's see how A is different. We have 10 meters, 20 degrees west of the south line. Again, start at the second one. We are starting south, and then we are heading in the westward direction. So then we pull this vector towards the west. We pull that 20 degrees. Now when I add this angle, notice how I'm making my angle with the vertical. I'm making it with the southern line rather than like in the first one where I made that angle with the horizontal. It's a very, very big importance that we're listing exactly where this angle is, and we're going to find out really quick in the next part of why that is going to be important. Notice the actual length of the vector. We don't need to, since we're only drawing one vector in each one of these, really it doesn't matter how long you draw it. Like, you're just going to put what the length of it is, and there's no other scale that you have to worry about, because each one is its own individualized thing. Now, obviously, if I was drawing the 10 meters and the 40 meters on the same plane, I would want the 10 meters to be like a fourth of the size. But since they're all being drawn on their own planes, you can draw it however long you want to. You're just going to list what the length of that is just by putting the 10 or putting the length around the actual error that you make. All right, and so like in the next one, we're going to do a length of 100. We're just going to draw a vector. It's telling me to start at my east line, but then I want to go 60 degrees south of that in the negative direction. So I want to go south, but negative south. So that just means let's go north. And I want to go 60 degrees negative south, aka 60 degrees north of still that eastern line though. So if we do get negatives, it's the first one that's being negative, but we still start at that place where it tells us to, which is the east line. So negative 60 degrees south is the same thing as 60 degrees north of the east line. We then add in our angle that we're connecting it to the horizontal, and then the length of this vector is 100. And the last kind of tricky one we might see is, what if I tell you it's 100 meters 90 degrees west of the north line? We'll start at the north line and then go 90 degrees in the west direction. Well, that gives me an entirely westward facing vector. So there's no real angle to draw here. Like, we don't need to connect it to anything because it's going just fully west. So I asked you like what this vector was. Another way you could write this exact thing is 100 meters west, and we don't really need that 90 degrees in there. All right, so please practice drawing these vectors. It's going to be very important that we can follow the instructions of how to draw a vector to making sure we know how to find its components, which is going to be part number 11. All right, in part number 11, we are going to be calculating the components of vectors. And so with the calculating components, a really helpful step is going to be to first visualize what this vector looks like. And so all of these examples are the same exact examples from part 10. And the first 9 questions on this page are also the same first 9 questions that you did in part 10. So this is for a purpose that you have already drawn these. So it's going to be helpful to go back and reference what this looks like when it comes back to finding these components. So imagine we didn't already draw it. You can redraw this again, but it's helpful to draw it so we can visualize what these components look like and visualize the trigonometry that we need to use to solve these problems. If you have never ever before seen trig, well, that's fine. We're going to figure out how to do some trig today. So trig is really not too complicated. We have some very basic trig statements, which are the sine of any angle is equal to the opposite over the hypotenuse. The cosine of any angle is equal to the adjacent over any hypotenuse. These are relationships that help us relate sides of a right triangle to an angle in that right triangle. And so why we want to sketch these vectors first is every vector, when it's at some angle like shown here, it's really just a right triangle, where if I draw the 2 sides of that right triangle, one of those sides is along the x-axis, one of those sides is along the y-axis, and we see like we have a perfect right triangle where one angle is 30 and we have a hypotenuse of 40. And the vector length itself, like the actual value, will always be the hypotenuse length. What we are trying to find in these problems is what is the value of Vx and what is the value of Vy, aka what are the components of this vector. So how we find the components is we will use both trig statements, and it doesn't matter which one you want to start with. In this case, let's just go ahead and start with the cosine. So the cosine of any angle is equal to the adjacent side divided by the hypotenuse. Notice our right triangle there. Our angle is 30 degrees. Our adjacent side, the side that is next to the angle, is Vx. My hypotenuse, always the longest side, is 40. So I've substituted in the angle, I've substituted in the hypotenuse, and I've substituted adjacent for Vx, which is the thing that we want to solve for. We then go ahead and rearrange this for Vx, and it says Vx is equal to 40 cosine of 30. Now this is where we can use a calculator to go ahead and tell us what is Vx equal to. And please take a moment right now before you move any further to make sure that your calculator is in degrees mode. So there's 2 modes for a calculator, radians and degrees. Make sure that you are in degrees because all of this page and the rest of this summer assignment needs to be set to degrees so we do a proper trig. So making sure that we are set in degrees mode, we then enter into a calculator 40 times the cosine of 30, and that it spits out that it is 34.6. That is how long that x side length of our vector is. And we've solved for the x component. Well, now let's solve for the y component. We used cosine to solve for the x, so we're going to use sine to solve for the y. Again, we start with the original identity, sine of theta is opposite over hypotenuse. We then plug in our angle, which is 30. The opposite side is the y component, and the hypotenuse is 40. Well, now we're going to do 40 times the sine of 30. Again, we plug this into a calculator. If we are in degrees mode, it just spits out that the answer is 20. And there you have it, our 2 components of this vector. This vector extends 34.6 meters in the x and 20 meters in the y. And that's actually a great way to think about like what are we solving for here, is think about this as a length measurement. Somebody told you to walk 40 meters, 30 degrees north of the east line, so you do that. Another person asks you, well, how far west, or how far east did you move? How far north did you move? Well, you moved 34.6 meters east, and then you moved 20 meters north. Like, we could get to the exact same position as instead of walking along the hypotenuse, like at that angle, you could just walk 34.6 east and then turn and walk 20 meters north, and you'd get to the exact same spot. And that's really what components are. They're just along the axes, how far did we move to get to the same location. All right, let's do the next example. We're going to start to notice the pattern here. So first we want to sketch this out, and this is what this vector looks like. Notice that this angle is measured from the vertical, and so if you're having hopes that, oh, we can just always do sine and cosine and they'll always be equal to the same components, not quite. So we can always do, like, we know we're always going to do sine and cosine, and we know we're always going to do like the hypotenuse times the sine of the angle and then the hypotenuse times the cosine of the angle, but it's not always guaranteed that like the sine is always x or the sine is always y. You need to sketch it out and see this triangle, make this statement. See, if we make this statement here, cosine is adjacent over hypotenuse. From the angle, my adjacent side, the side next to the 20, is the y side. In the last case, the y side was the opposite. It matters how you draw the angle, which side is opposite and which side is adjacent. So it is very helpful to visualize the vector for that reason, to see what the sketch is, draw the right triangle as it's given. So you make sure that you're pairing the right y with the right trig statement. So in this case, when we solve this for y, we are going to do 10 times the cosine of 20. And the other reason why it's extremely important that we draw these vectors is that we need to indicate if we moved backwards or if we moved it in a negative direction for these components. So what I mean by this, I mean there's two ways that we can move in the y direction. We can move up in the y or we can move down in the y. And by convention, up is going to be what we're going to call positive, like we did in the first example with v. But in this case with A, we are moving down, and we are moving down 9.4 meters. Now that negative is not going to come up in your calculator. You need to see that that V is going down, especially when we draw it, and make sure that when we are entering the answer, that we are going to call it negative 9.4. And that's going to be very important, as we're going to see as we move forwards, to both making sure that we are drawing our vectors the right way and to make sure that we're adding our vectors the right way. So components are negative if they are in the opposite directions. So a quick way that you can verify this is if we have any direction, anytime we see a south in any of our problems, then that component, the y component, needs to be negative. And anytime we see a west, that x component needs to be negative. So if you notice in our first example, we had north of east. North is telling me my y should be positive. East is telling me my x should be positive. But in the A, we have west to south. So west is the negative x direction, so my x should be negative. And south is the negative y direction, so my y should be negative. All right, so finishing this up, let's go ahead and solve for the x. We're going to use the sine to get that, and we're going to do 10 times the sine of 20. That's going to give me a number that's not negative, but we're going to make it negative because visually we can see that we're moving backwards in our x direction. We're moving backwards at 3.4, or we'll call that negative 3.4. All right, moving on to the next one. Again, I'm going to start to move quicker here because what we are always going to end up doing, so we sketch it. We draw our components, our x and then our y. We are always going to end up doing like the hypotenuse times the sine and then the hypotenuse times the cosine with the angle in there. Still draw it to make sure that we're going to use the right one for the right thing. So like in the x case, so if I start with the cosine, x is the adjacent side, so 100 times the cosine of that angle will be my x, and that is going to be positive. And then 100 times the sine of that angle is going to be negative. If you'd like me, I just had a second here. I was like, why did we go upwards? Because it's negative 60 south, which is really the same thing as north. So if it's negative south, we end up still with a positive y exponent. And so my final answers are just positive 50 and positive 86.6. But still, very much so, you're always going to do hypotenuse times cosine, hypotenuse times the sine of those angles. But you got to make sure you're putting the right component, so which one of these is the x and which one of these is the y. The way you figure that out is draw it out, figure out which component is opposite, which one is adjacent. All right, and then our last one is a bit of a trick question. So if we draw this vector, as shown here, we have 100 meters directly west. Well, how can I do a sine or a cosine? Am I going to use the 90 degrees here? Am I going to do like 0 degrees here? You don't have to do anything, because if I tell you that we are moving 100 meters west, well, that's entirely in the x direction. Another way to list this is move all the way 100 west, negative 100, and then don't move any which way in the y direction. So if a component is, if a vector is perfectly along an axis, then you don't have to do the trig, then all of that will just be right in there. All right, and that's our final answer. All right, that is how we calculate the components. And then in our next part, we're going to see what happens when we start with components. How can we do the reverse in part 12. In part number 12 here, we are going to be calculating the magnitude and the direction of we're going to calculate magnitude direction when we are given the components. So this is the exact reverse of what we did in part 11. In part 11, we were given magnitude and direction and asked to find the components. Well, components contain all of the information about a vector. So there's two kind of ways that we express vectors. Either the kind of straightforward way, which is magnitude and direction, or you can express a vector in the components. But you have to be able to go from one of those to the other, because both are like full and complete information about the vectors. So if I tell you that we have a vector A has an x component of positive 4 and a y component of 8, what would that vector look like? Well, that would look like us going positive 4 in the x direction, and then upwards 8 in the y direction. But then that vector would be the length of going straight from the origin where we started up to the end of the arrow for 8 to where we ended. So that's what that vector looks like. We can go and label that vector A. And notice I'm using the notation for a vector, which is to put the arrow above the letter. And then we can go ahead and label the angle that we're going to calculate here. So how would I figure out, so what I'm looking for is what's the length of A and what is the angle theta. So how would I figure out the length? Well, that is really easy because we just need to use Pythagorean theorem for that. We are looking for the hypotenuse of a right triangle when we know it's 2 legs. So we're going to do the square root of 4 squared plus 8 squared, which comes out to be 8.9 meters. So that is the magnitude of A. That is how long a vector A is. But what is the direction of A? We're going to do a little bit more trigonometry here and just solve for an angle. So any trig statement, we usually list that if, like, say, sine of an angle is equal to the opposite over hypotenuse. If you want to solve for the angle itself, we have to do the reverse trig statement. And the one that's going to be the most useful for us here is using the inverse tangent. And make sure we are doing tangent to the negative first power when we do this. But inverse tangent of the opposite side over the adjacent side. So from my angle that I drew in the picture there, the opposite side of that angle is 8. The side next to the angle, the adjacent, is 4. So I'm going to do inverse tangent of 8 over 4. And when we're entering this into the calculator, don't just like try to raise your answer to the negative first power. It's usually on a second. You do second tangent to do tangent to the negative first power. Then parentheses, you can do 8 over 4. You could also just simplify that and do inverse tangent of 2. We get the same answer. And then you're going to get 63 point whatever. You're going to notice I'm going to round all of my angles to just the whole number because they're angles, like there's 90 of them in one decimal. We're not trying to be that accurate. You could go to 3 decimal places. You could go to 1 decimal place, 2, 3. I'm just going to round them all to just the whole, to the 1 spot. All right, and so that is the angle that is given, or that's the angle that we get out of the calculator. But for our final answer, we want the magnitude and the direction. The direction is certainly not just 63, but how is that 63 from where? And so we are going 63 degrees north of the east line. Again, that comes back to making sure we understand how to draw vectors, but that vector, that angle, is above the east. And so it is north of the east line. Make sure that we give all parts of this, both the length and the angle and the directions of that angle. Now let's see this again for W. We first want to sketch this. So we're going to go in the positive 3 in the x-axis. and then negative 5 in the y-axis. We are then going to connect and show what we are measuring here. And so W is the hypotenuse between this 3, 5 triangle, and then the angle is shown here. So the length of W, we are just going to use Pythagorean theorem. We do the math, and we see that that length is 5.8. And then for the angle, we do the inverse tangent again. We're always going to do inverse tangent. We're going to do of the opposite side over the adjacent side, so a 5 over 3. And then putting it all together, that's going to be 5.8. It's going to be at an angle of 59. And then think about what direction is this in. We're starting at the east, and we're going south of it. So we're going south of the east line. That is the angle given. Now, as I keep going here, you notice two things. One is, or the one big thing is that as I draw my vectors, I would say it's conventional to always draw the x and then to draw the y. So what I mean by this is for the m, I'm going to do negative 4 in the x first, and then from that negative 4, I'm going to do negative 4 in the y next. So we did the x, and then we did the y, and then we connected them. Now, really, and that's going to mean that the angle I'm measuring is measured from the west line, and then I put just the length on the hypotenuse of it. Now, there's no reason that we couldn't have done this the other way around. And for this case, it's especially we would get the same thing because we're just going to go 4 down and then 4 over. But my theta would be on the other side here. So it's conventional to do x and then y, but you don't have to do x and then y. But if you always do the x first, so let's go ahead and get what their statement is. We're going to get our magnitude will be 5.7. But if we always do the x first, what we're going to ensure is that we will always be measuring from the east line, or we'll be measuring from the south line. So all of our answers will end up being either north or south, and then either east or west, rather than the reverse of being east of the south line or west of the north line. Okay, in this case, we still go ahead and figure out what is that angle by doing inverse tangent of 4 over 4. Inverse tangent of 1 is exactly 45 degrees, which makes sense because this is a special kind of triangle with two legs are the exact same. So in this case, how I drew it, again, we get the magnitude of 5.7, but 45 degrees south of the west line. Again, the south, it's the y direction, and then of the x direction. And again, we could, in our next case, choose to do 10 and go up 10 and then backwards 3, but it's pretty standard to go backwards to do the x first and then to do the y. Connect the two, throw the angle in there, show what we're measuring with k. The magnitude of k is just going to be Pythagorean theorem, and then the tangent, inverse tangent always of the opposite side of the adjacent side. Again, by doing it x then y, you always want to just list, okay, did we go north or south first? And then second, was that of the west line or of the east line? So in this case, we went north, and then we went north of that west line. And that is our final answer. All right, and that is everything for part 12. Right, part 13 is our last part of vectors, and in this part we are going to add vectors together. So when you add any two vectors together, we usually call what we get the resultant. So as we see here, we use the symbol R to represent the resultant, and R is just the sum of those two vectors. Now one way we can add vectors is what's called the tip to tail method, and that's shown graphically with our vectors A and B up in the right hand corner there. So we're seeing we draw A, and then we draw the tail of B on the tip of A, and then we can keep adding vectors, and then we're always just connecting our very start point to our very end point. Well, that's vector R, the very start point to the very end point. But what's really helpful is rather than drawing this graphically, it's just to add the components together. So when I want to add vectors A and B, I really just need to add the values of X with the values of X and the values of Y into the values of Y. So for our first example, we have an X value for A of 3 and an X value of B of 4. So I get an X value of AB of 7. We do the same thing with the Y's. We get 6 and negative 1. And then 6 plus negative 1 is going to give us 5. So I'm just adding the X's with the X's and the Y's with the Y's. So that is the final resultant components. And then we're going to go ahead and draw this vector. And so they're both positive, so we go forward 7, upwards 5. Our resultant is then the starting point to the ending point. we'd label that r, and then go ahead and find the magnitude and direction of that resultant vector. We find the magnitude and direction exactly like we did in part 11 or in part 12 by doing a Pythagorean theorem to get the magnitude. So that'd be the square root of 7 squared plus 5 squared. And then we'd find the direction by using the inverse tangent. In this case, that's inverse tangent of 5 over 7. Make sure that we represent that angle. We give the directions of that, and in this case, that is measured north of the east line. And so altogether, that is the resultant vector of A plus B. Do the exact same thing for B and C. We add 4 with negative 5 to get negative 1, and then we add negative 1 with 3 to get positive 2. Sketching this vector, we're in the negative for our x, backwards 1, and then we're in the positive for our y, upwards 2. We connect those two, and that is the resultant. The magnitude of that resultant is going to be 1 squared plus 2 squared. Take the square root of that. That's 2.2. And then the angle would be inverse tangent of 2 over 1. That's 63 degrees, and that's north of the west line. For the third one, we're now subtracting. We're not going to see a lot of these, but if we were asked to subtract, then you just subtract the components. So starting with A, our x component is 3. Our x component of C is negative 5, so we're going to do 3 minus negative 5, and that gives us positive 8. For our y, we do 6, and then minus 3. 6 minus 3 is 3. So we sketch this vector. That's forwards 8, upwards 3. We then draw this magnitude by connecting. That's the resultant vector r. The magnitude of r would be 8.5. The angle of r would be 21 degrees north of the east line. And then lastly, the most tricky one is when we come across wanting to add vectors where we only have the magnitude. So if we have a plus d, how do I add vector a with vector d if I don't know what the components of d are? Well, we're not given the components of d, but luckily we know how to find the components of d by following the steps outlined in part 11. So in part 11, we saw that to find the components, we want to sketch this vector. Once we sketch it, we turn that into a right triangle, and then we use sine and cosine to get our components. In this case, the 10 times the sine of 30 is going to give us the y component, and 10 times the cosine of 30 is going to give us the x component. Also, by sketching, we see that we're going downwards, so our y component should be south. We're going forwards in the x direction, so our x component should be positive. So altogether, that gives us a final two components for d to be 8.7 in the x direction and negative 5 in the y direction. Lastly, we then want to do what we set out to, which is to add a and d together. So to add their x components, our final resultant will be 3 plus 8.7 to get 11.7, and then 6 plus negative 5 to give us positive 1. We then sketch this. Both are positive. We go forwards 11.7, upwards 1. R is then the connecting those two. The magnitude of R is going to be 11.7 with an angle of then 5 degrees, and that is measured north of the east line. That's all there is to sketching vectors. Next up with part 14. Part 14, 15, and 16 is where we're going to get into some actual physics here. And so we're going to keep it pretty basic with just some simple questions asking about the motion of objects. And so, as we'll find with physics, often we're given a lot of information, and a lot of physics is just making sense of that information. So, for example, with these problems, we're given some information. We're asked to figure out the four most basic parts of these objects' motion, which are what is their distance, displacement, speed, and velocity. So, distance is the total length that is actually traveled by an object, while displacement is how that object's position changes over its time being, and they are not always the same, and often they're very commonly not the same, especially when we're moving in multiple directions. So let's just see this in example. In the first example here, a ball rolls 4 meters forwards, then 2 seconds, 10 meters backwards in 4 seconds, then 22 meters forwards in 10 seconds. Great tip for now and the rest of physics is, can we visualize this problem? Great tool to help us visualize is just to make a little number line. Really, you don't need to be exact with this number line. I'm not even going to put like real values on it. I'm just going to pick a place to start, and I'm going to visualize moving 4 meters forwards because that's what this ball does. But then this ball turns around and moves 10 meters backwards. So from that point of where I ended my 4 arrow, I'm going to make an arrow that is 10 backwards. Again, notice I'm not even using my number lines to help guide me here. I'm trying to make my arrows like size relevant, where like the 10 was a bigger error than the 4, but it doesn't need to be perfect. We're just helping to visualize where we're starting and then where we're going. So then after we move 10 backwards, we then turn around again and go 22 forwards. So our ending point is over here. So when I ask the question of what is my total distance rolled by this ball, well, it rolled 4, and then it rolled 10, and then it rolled 2. So we never really indicate or care about the direction. We just add up all of the individual results, which in this case is going to be 4 plus 10 plus 22 to get a distance of 36. So that's how far this ball actually moved or actually rolled. But how far did this ball end up from where it started? That's different than 36 because it's currently not 36 meters away from where it started. It is a distance of the S from the E to where it started. All right, before we get to the displacement, our speed shown here is just our distance traveled divided by the time it took. So we added up all of our 4, our 10, and our 22 to get 36. Now we're going to add up the times to get 2 seconds plus 4 seconds plus 10 seconds to get a total of 16 seconds for our time. And then 36 divided by 16 is 2.3. That is the average speed that we traveled at over this time period. Now for the displacement, we are looking for the distance from the starting point to the ending point. So if we have a really nice number line and we kept track of exactly what that ending point was, we could do it that way. But we can also just figure out what the displacement is by taking into account which of these were forwards and which of these were backwards. So in total, I went 26 meters forwards, and I'm just adding the 4 and the 22. But then in total backwards, I went 10. So I went 26 forwards, and then I went 10 backwards, or that's a total of 16 forwards is the net result of this motion here. So my ending point is 16 meters ahead of that starting point. And that ahead or that direction is important to the displacement that we want to indicate forwards or backwards often. So my displacement is 16 meters forwards as indicated with the arrow. And then my velocity is just that displacement divided by time. So 16 over 16, it's the same time. The time for the distance is always the same time for the displacement. Yeah, the time for the speed is the same as the time for the velocity. It's only ever one time. But often the speed will be different from the velocity because we're using different values for the distance and the displacement. So a way to think about these two numbers is the speed is actually how fast this thing was really moving. It moved with an average speed of 2.3, in all the actual motion of it. But if we ask our question, how good was this ball in getting forwards? If the net result was just to get 16 meters away, how good was it? And in average, it was moving kind of slow at only 1 meter every second because it spent time not only going forwards but going backwards. So if we're measuring the effectiveness of it moving forwards, it's not as effective at doing that when if we're measuring just its total effectiveness of motion as being 2.3. Okay, so with all 4 measurements, we get a clear picture of what this thing was doing. Just one measurement of distance doesn't paint us the entire picture, but both measurements of distance and displacement, we got a clear idea of what's actually happening in motion. Okay, let's see this again for our next example, which is just a little bit more complicated. So again, visualizing this is very helpful, but we have to visualize this a little bit differently because we're not being told how far they're moving. We're being told points that this cart is moving to. So just like before, I'm going to pick a point to call my starting point, and it says that it starts at x equals 0 and then moves to x equals 14. So that is a point on the number line. That is not necessarily the length of the arrow like it was last time. Then I'm moving, so obviously the length of that arrow is going to be 14, but in my next case, I move from 14 to 22. That is not saying it moves 22 meters. It's saying it moves from the point 14 to the point 22. And then we move backwards to the point negative 20. That arrow is not negative 20. The final position of it is negative 20. Okay, so when it comes to finding distance, what we're not going to do is add 14, 22, and 20 because those are not my distance arrows. The first arrow is 14, but then if I move from 14 to 22, well, that's a distance of 8 because that's just the difference between 14 and 22. And then if I move from positive 2 all the way back to negative 20, well, I'm going to move 22 meters to get back to 0, and then an additional 20 meters to move back to negative 20. Or we could say that's a total length of 42. So now when it comes to finding my entire distance, now these are the three numbers that I'm going to add together, 14, 8, and 22. And that's going to give me a distance of 64. Again, to find the speed, we just do the total distance over the total time. So we add up all of those time values. The first is 5 seconds, and then 2 seconds, and then 8 seconds. So that's a total time of 15. So my speed's going to be 64 over 15, giving me a final value of 4.3 meters per second. Now for my displacement, this one's a lot easier than the last one because it's just given to us. I start at 0 and I end at negative 20. So in total, how far is my starting point from my ending point? Well, it is backwards 20. So my displacement is negative 20. We can also and often do refer to this as negative 20 or as 20 meters backwards. And you have the freedom to do either of those, but don't do both. So it is either negative 20 meters or it is 20 meters backwards. Those are the same equivalent. And then lastly, for velocity, we do our displacement over our time. It's the exact same time, but now it's negative 20 over 15. So that simplifies to negative 1.3 meters per second, or again, 1.3 meters per second backwards. Okay, so a lot of part 14 is just sketching out this motion and then putting all of the pieces together to get the distance, displacement, speed, and velocity. All right, next is part 15. And in part 15, we are doing the same kind of distance, displacement, speed, and velocity values, but now we're going to up the difficulty a little bit by adding an additional degree of freedom. So now, rather than just limiting our objects to only moving forwards and backwards or along a one-dimensional plane, now they can move both forwards and backwards and left to right, or they can move both north and south and east to west. So like last time, it's very helpful to sketch this motion to kind of get the full picture. So let's just do that for our first example. A man walks 50 meters north. If you notice on my coordinate system, I don't have 50 meters on here, but I do. It goes from 0 to 6 in all directions. So I'm just going to represent that 50 by just going up 5. I'm going to think about that as being times 10 bigger than what it actually is. I then am going to move 40 meters west. So then in the western direction, I'm going to move backwards 4, call that 40. And then I finally move 20 meters south. And so I'm going to go down 2 and call that 20. Now, when it comes to the distance, all we ever care about is just the total number of steps taken. In that case, that's going to be 50 plus 40 plus 20, giving us 110 for our distance. Likewise, for the speed, all we got to do is that total distance over the total time. So my total time is going to be 5 seconds plus 8 seconds plus 2 seconds, so a total of 15 seconds. So 110 divided by 15 gives me 7.3 meters per second. But now when it comes to the displacement, how far is my starting point from my ending point? Well, let's represent that and call that length, that arrow, delta x. That's what I'm trying to find. So what is the length of delta x? Well, one way that we can find this is using those vector values that we just worked on in parts 11, 12, 13, and 14. And so we have a vector arrow is moving backwards 40 in the x direction and upwards 30 in the y direction. So what I just did there was make a right triangle where I know the two legs and I'm looking for the hypotenuse. Well, that hypotenuse I can find by using the Pythagorean theorem. So I can do the square root of 40 squared plus the square root of 30 squared, and that gives me the square root of that gives me 50 as my final answer. And then to find the speed, so that's how I get the displacement, the magnitude of the displacement. To get the velocity, we again just divide that number by the total time of 15, comes out to be 3.3. But both the displacement and the velocity need a direction to it because both are vectors and both then have a direction. How do I figure out the direction? Well, that's where we use the inverse tangent of my opposite over my adjacent. So in that case, this can be inverse tangent of 30 divided by 40. Gives me an angle of 37. We, looking at this triangle, can see that that angle is measured north of the west line, and then that angle or that direction is paired with both that displacement and that velocity. Both, and the displacement and velocity will always be in the same direction. So we only have to like do the calculation once. The magnitudes of them are different, but same direction always. All right, and that's how we do the 2D problems. So let's see this again. It's really no different for the next one. We're just adding more steps to it. So a hiker moves 4 south, so we sketch that, and then 5 west, and then 10 north, and then 8 east, and then 2 south. And so often I think the trickiest part is just making sure our sketches are good and they are to scale. Just make sure that we're counting slowly, and we're ending up at the points that we start at. But always when it comes to distance, we're just adding each one of those numbers. So we're adding 4 plus 5 plus 10 plus 8 plus 2 gives us 29. We're then dividing that by the time, which is 15. So 29 divided by 15 is 1.9. Then when it comes to the displacement, always connect the starting point to the ending point. And if you noticed in both of these examples and in all of the problems that you should do, just start at the origin. And so we're always going to connect that 0, 0 to wherever our point ended at. Then we are going to turn this into a right triangle. In that case, we're going to go how far in the X direction did we go, how far in the Y direction did we go, and boom, we have a nice little 3, 4 triangle. And then that means our displacement is going to be 5. Because that's just the Pythagorean theorem. It's a 3, 4, 5 triangle. And then our velocity will be 5 over 15, so 0.33. And then do not forget the direction for our displacement and our velocity. Same direction for both. And we would get that by doing inverse tangent of 4 over 3, giving us 53 degrees north of the east line in this case. All right, so that is how we find all of the motion variables for 2D motion. All right, and that is the penultimate section, and now on to the very last. Our last section is part 16, and this is just some word problems for you. These are just 2 examples, and you'll notice through the rest of them, like they take on a variety of shapes. Like no really 2 word problems are the same, but this is just some practice for you of identifying what do we know and picking the correct equation of what to solve for. And so let's just go ahead and see that in action. So in our first example, a train is traveling at an average speed of 30 kilometers per hour. How far does the train travel in miles after 3.5 hours? So a helpful practice is just to list what do we know. We know the speed of this train is 30 kilometers per hour. We know that the time is 3.5 hours, and we're asked to solve for what the distance traveled is. How far does it go? Well, distance, if we see that equation, is just speed times time. So we can just multiply our speed and our time, and that's going to give us the value for distance of how far it goes at that speed in that time. Notice I'm chugging along with the unit values here to show you that when we do this calculation, hours does cancel and kilometers is what we have left over. 105 kilometers is how far this train goes. This train asks, though, for how far in miles does it go. So a lot of these word problems just have an extra little bit of pizzazz just to up the difficulty a little bit. So how do I change this to miles? Well, we would go back and look at section 3, our unit conversions, our standard unit conversions, to see how do we go from kilometers to miles. And so do a standard unit conversion, and that the table will tell you that 1 mile is 1.6 kilometers. So we just want to then convert correctly, and we would correctly convert by dividing by 1.6, that our distance is really 65.6 miles. And then that is our correct final answer. All right, same thing in the next one. We're given some information. A cow runs at a velocity of 5 miles per hour to the west. How long does it take the cow to move 30 meters west? So the first thing I'm going to do is identify whether our velocity given to us is 5 miles per hour west. I know it's a velocity because I had direction. I'm wondering how long does it take to move 30 meters west? And so the first thing I'm going to do here is, rather than combine these, because I really can't yet, if I have miles per hour and I have meters, we can't combine them in any way to get something usable because our units are not going to cancel out. So what I'm going to do is change 5 miles per hour, and I'm going to unit convert that to meters per second. I'm going to, just like in part 3, set up a conversion factor. I'm going to end up multiplying by 1609. I'm going to divide by 60, and then I'm going to divide by 60, and that gives me the value of 2.23 meters per second. Now, why did I change that one? Could I not have changed the distance? Sure. I could have, instead of changing the miles per hour to meters per second, I could have changed the 30 meters to miles. In this case, though, it's going to make more sense to change our speed measurement to meters per second, not just to change the meters so they cancel, but to also get out of this hours, because if we didn't convert out of hours, this would have been an extremely small amount of time in terms of hours. And I know that because my final answer is 13.5 seconds, which if we would convert that to hours would be like 0.000 some hours. So if we were to do this problem, get a final answer in like 0.000 some hours, maybe it'd be a good idea then I'd be like, oh, I should probably convert that to seconds, which is what the problem didn't necessarily say it had to be in seconds, but always a good idea to express our units in values that make sense to us, especially for these last few problems here. All right, that is the end of this summer assignment. If you made it to the end of this video, thank you for listening, and I hope that this summer assignment is going well for you. If you have questions on any parts of this, please feel free to reach out to your teacher, and I hope you the best and as you are trying to master this physics knowledge. Looking forward to seeing you at the start of the school year.